Hello friends, let us now learn some important points about the scatter radiation. So, if you see the scatter radiation, our discussion of attenuation has only dealt with primary radiation. This primary radiation is a radiation which either passes through the patient unchanged or is completely removed from the useful beam. The primary radiation carries the X-ray image. Now the problem is scatter radiation or secondary radiation. So this scatter radiation detracts from film quality, it detracts or decreases the film quality and contributes no useful information. How important is scatter radiation? How much density of an X-ray film is from scatter radiation? Several factors determine the importance of scatter radiation. Frequency making up from 50 to 90% of total number of photons emerging from the patient is scatter radiation. The reason for the large number of scattered photons will be more apparent if we consider the fate of diagnostic X-ray beam. So this is the X-ray beam. If the X-ray beam passes through thicker body parts like abdomen, only 1% of photons in the initial beam reach the film and the rest 99% are attenuated, majority by the Compton scattering. So most of them do not reach the film. Nevertheless, those that reach the film make a major undesirable contribution to form film blackening. So undesirable radiation is the secondary radiation which causes film blackening. It would be more accurate to refer it would be more accurate to refer all undesirable radiations as secondary radiation, which includes protons and electrons and contribute to film fog. In actual practice, none of the electrons have enough energy to reach the film, and the only characteristic radiation with sufficient energy to cause a problem occurs during contrast examinations like barium and iodine. So none of these radiations or film for secondary radiation do not have energy to reach the film. In contrast examinations like barium and iodine, the secondary radiation, that is the characteristic radiation, have enough energy to reach the film and result in problems. The only significance of secondary radiation of any significance comes from Compton scattering, and it has become common practice to refer all undesirable radiation as scattered radiation. Now, let us learn the factors affecting scattered radiation. Three factors determine the quantity of scattered radiation. They are kilovolt peak, path thickness, and field size. Scatter radiation is maximum with high KVP techniques, larger field size, and thicker parts. Unfortunately, this is what we usually deal in diagnostic radiology. We rarely have control over the thicker part thickness, and frequently we must use large field size. So we must use large field size and thicker parts cannot be controlled. So the only variable we can control is KVP. But even here we have less control than we would like because patient doses increases sharply with low KVP. First, let us learn about the field size. Field size is the most important factor in production of scatter radiation. This is an X-ray tube. An X-ray tube irradiates the patient. So this is the X-rays. So the X-rays transmit through the patient. Some of them are attenuated and they produce scatter radiation. So when an X-ray tube is collimated in order to produce thin small volume of tissue or if an X-ray tube is collimated, this results in production of narrow beam of radiation which will irradiate a small volume of tissue. It generates small number of scattered photons. Most of the scattered photons miss the film because most of them will have larger angle of escape. Because of larger angle of escape, most of the scattered photons will miss the film. So narrow beams X-ray field irradiates small volume of tissue as it generates small number of scattered photons, and these scattered photons have large escape angle, so they never reach the film. So if you see, this is the X-ray tube, this is the collimation, and this is the smaller, thin narrow beam, and here the patient is there. So this is the angle of escape. The angle of escape for a scattered radiation is this point, is the angle of escape. So thus the quantity of scattered radiation from a narrow beam is small to begin with, and most of it never reaches the film. As the field size increases, scattered radiation will increase. So for this reason, narrow beam attenuation is the method used to measure the attenuation of primary radiation. The term narrow beam and primary radiation are used synonymously. Then, as the X-ray field is enlarged, the quantity of scattered radiation increases rapidly at first, and it gradually tapers off. So first, as the field size increases, the scattered radiation will increase first, and then gradually it tapers off until it reaches a plateau or saturation point. Further increase in field size has no effect on the quantity of scattered radiation. Beyond the saturation point, further increase in field size has does not change the quantity of scattered radiation reaching the film. So the quantity of scattered radiation remains constant. The total number of scattered photons increases, but the number that reaches any particular point on the film will be constant. Next, the second important thing is about the part thickness. The quantity of scattered radiation reaches a saturation point with increasing part thickness. So with increasing part thickness, the scattered radiation also increases, and then it reaches a constant point. The total number of, as part thickness increases, scattered radiation increases up to a certain point, followed by which the thickness will reach a saturation point. The total number of scattered photons keeps increasing as the part becomes thicker. But the scattered photons which are originating from the upper layers of the patient, if the scattered photons are originating from the upper layers of the photon, this scattered radiation do not have energy sufficient to reach the film. Unfortunately, we have little control over the part thickness. So these do not have the energy to reach the film. Okay. The third property is kilovoltage peak. The effect of kilovoltage peak on the production of scattered radiation is probably not as important as part thickness, and certainly is not as important as field size. Low energy range, that is 20 to 30 kilo electron volts, here photoelectric effect predominates. Extremely little scatter is produced when in low energy range, but as the radiation energy increases, percentage of Compton scattering increases, and so does the scatter radiation increases. So Compton scattering increases as the KVP increases. After Compton scattering becomes predominant interaction, scatter radiation production also tends to plateau out, just as does with increasing field and part thickness. The energy of the point at which this plateau occurs depends on the atomic number of the tissue. But this plateau is not well defined as it is with field size or part thickness. Even after the Compton reactions predominate, the quantity of increase in scattered radiation continues to increase with increase in beam energy, because more photons scatter in forward direction, and their energy allows them to penetrate greater thickness and greater thickness of tissues to reach the film. Because we have little control over the production of scattered radiation, we must find the ways of keeping it from X-ray film after it is being generated. Thank you.